Assalamu alaikum, brothers and sisters. Welcome to the journey of quest, where we quench your thirst of knowledge. Have you ever fantasized about traveling to distant galaxies in a blink of an eye? What if the universe has hidden shortcuts? Imagine folding a piece of paper with two dots on opposite sides. By bending the paper, these dots can be brought instantly close, even though they are far apart on the flat surface. This is the basic idea behind wormholes, theoretical tunnels through the fabric of space-time, connecting distant regions or even different universes. Wormholes captivate both the minds of astrophysicists and the imaginations of science fiction writers. Envisioned by Albert Einstein and Einstein-Rosen in the 1930s, these cosmic phenomena are not just flights of fancy, but grounded in the equations of general relativity. They suggest that these shortcuts could exist, allowing for instantaneous travel across vast cosmic distances. This notion isn't just science fiction. Today we delve into the real science behind wormholes. To grasp wormholes first, we need to understand the fabric of the universe itself, space-time. Imagine the universe not as a vast emptiness speckled with stars, planets, and galaxies, but as a dynamic four-dimensional fabric. This concept, central to Einstein's theory of general relativity, revolutionized our understanding of how the universe operates. According to this theory, what we perceive as the force of gravity is actually the bending of this space-time fabric caused by the mass of objects. Let's use a simple analogy. Picture a large, stretched-out sheet of fabric. When you place a heavy ball on it, the fabric will warp, creating a dip or a curve. Now, if you roll a smaller ball near the curve created by the heavy ball, it will spiral towards it, not because there is a direct force pulling it, but because it's following the curve of the fabric. This is akin to how planets orbit around stars, including how Earth orbits the Sun. Every star, every planet contributes its own dip and curve to the fabric of space-time, influencing the paths of nearby objects. This interconnected dynamic web of dips and curves underpins the cosmic dance of celestial bodies. Now imagine bending this fabric so much that 2 points touch. That's where the idea of a wormhole begins. What exactly is a wormhole? Let's dissect its structure. Imagine, if you will, a tunnel with two ends, each opening into different points in space and time. This is the basic structure of a wormhole, comprising two key components, the mouths and the throat. The mouths of the wormhole are like doorways, entry and exit points located potentially light years apart or even in different universes. Connecting these mouths is the throat, a tunnel through which information, matter, or even a daring traveler could hypothetically pass. In the realm of theoretical physics, wormholes are fascinating not just for their structure, but for their varieties and the unique properties each type possesses. There are primarily three types of wormholes: Schwarzschild wormholes, traversable wormholes, and non-traversable wormholes. Schwarzschild wormholes, often referred to in scientific circles as Einstein-Rosen bridges, are the simplest kinds of wormholes. They theoretically connect two different regions of space-time. However, they have a significant limitation. They collapse too quickly for anything to travel through them. The moment matter tries to enter one end, the wormhole collapses, making it impossible for anything to pass from one side to the other. Then there are traversable wormholes, which are far more promising for the sci-fi dream of space travel. These wormholes are theorized to stay open long enough for travel between their mouths. But here's the catch. Keeping a traversable wormhole open requires something known as exotic matter. This exotic matter must possess negative energy density and large negative pressure, properties not typically found in conventional matter. Lastly, non-traversable wormholes, as the name suggests, are types that cannot be crossed. Think of them as blocked tunnels where only certain types of information or energy might pass through under specific theoretical conditions. While Schwarzschild wormholes collapse rapidly, traversable ones, which are more suitable for travel, need exotic matter to stay open. This intriguing requirement not only challenges our current understanding of physics, but also ignites the imagination about what could be possible in the far reaches of future technology. Stabilizing a wormhole requires something extraordinary: exotic matter. Now let's dive into what this means. Unlike the everyday matter that makes up the stars, planets, and everything visible around us, exotic matter has properties that seem to contradict the very fabric of physics as we understand it. Exotic matter possesses what's known as negative energy density. Imagine a material so bizarre that instead of being pulled by gravity like everything else, it repels it. This characteristic is crucial for the concept of traversable wormholes. Typically, a wormhole's throat, the narrow bridge between two separate points in space-time, would naturally collapse under its own gravity, much like a tunnel with no supports will cave in. However, exotic matter acts like these necessary supports, pushing outwards and keeping the wormhole open. Now let's touch on some fundamental physics. In general relativity, we have something called energy conditions. These are rules that, broadly speaking, restrict the behavior of matter and energy in the universe. One of these, the null energy condition, posits that in any frame of reference, the energy density along rays of light or other null paths should be non-negative. Exotic matter, with its negative energy density, flagrantly violates this condition. This isn't just a minor infraction in the cosmic rulebook, it challenges our understanding of the very principles that govern the universe. The existence of exotic matter is still hypothetical, but without it, wormholes might remain forever impassable. Harnessing wormholes could revolutionize space travel, but what challenges do we face? The concept of wormholes tantalizes with possibilities, yet the path to turning these theoretical tunnels through space-time into reality is strewn with formidable obstacles. First, consider the technological Herculean task of detecting a wormhole. Given that no empirical evidence of wormholes exists to date, the initial challenge lies in proving they are more than just elegant mathematical constructs. This requires advancements in technology far beyond our current capabilities, perhaps leveraging quantum computing or yet-to-be-invented methods of space-time manipulation. Once detected, the next hurdle is stabilization. Wormholes, by their very nature, are predicted to be highly unstable. They might collapse so quickly that even light, the fastest traveler in the universe, cannot pass through them without being crushed. Theorists suggest the use of exotic matter to keep the wormhole open. This exotic matter would need to have negative energy density, an unusual and largely theoretical form of matter that we have yet to observe or create in any sustainable way. Furthermore, even if we manage to stabilize a wormhole, there are profound theoretical issues to tackle, such as the causality problem. If information or matter could travel instantaneously through a wormhole, it might violate causality, leading to paradoxes where cause and effect become indistinguishable. This not only challenges our understanding of physics, but also the very nature of time and reality. The journey to making wormholes a reality is fraught with hurdles, both theoretical and practical. The quest for wormholes is not just about reaching distant stars. It's a journey that plunges into the very fabric of reality, challenging and expanding our understanding of the universe. As we continue to explore this fascinating concept, the implications for physics, particularly in the realms of quantum mechanics and general relativity, are profound. Imagine for a moment harnessing the peculiarities of wormholes to bridge not just spatial, but informational gaps across the cosmos. The study of wormholes could revolutionize the way we think about space and time, offering insights that are currently beyond the reach of conventional physics. This exploration might lead to a new understanding of quantum entanglement and the spooky action at a distance that baffled even Einstein. Moreover, the potential of using wormholes for instantaneous communication is a tantalizing prospect. Imagine sending information across thousands of light years in the blink of an eye, transforming interstellar communication and making the vast universe a little more navigable. This could dramatically accelerate the pace of space exploration, allowing distant probes to send data back to Earth instantaneously, or enabling real-time control of rovers on far-off worlds. Such advancements could also lead to unforeseen technological revolutions here on Earth, perhaps in the way we compute or in the creation of highly efficient, super-fast communication networks. The possibilities are as limitless as they are thrilling. Whether or not wormholes will ever be traversable, their study pushes the boundaries of our understanding of the universe. Thanks for watching us share our videos. Subscribe our YouTube channel and press the bell icon and stay curious for new uploads.